recording back while I was recording, so you get what's going on here. I'm playing back a movie or an audio or both, and while that's all happening, I'm recording everything on the desktop, and that was like, it was a little overwhelming for the computer, and so I just avoided that this time by showing you what I wanted to play and then recording after that. So last time we finished up the 8.6 thing where we had all kinds of things. We had topology. We started playing around with Möbius strips. We learned about the term genus. We had different kinds of geometry, as in hyperbolic and elliptic, and then good old plane geometry. We also learned about networks, whether networks were traversable or not. So I'm wondering if you have questions on anything from that assignment, either the assignments or just in general. I think I have some of them on my sheet.
11.
Okay. See if I got that one. How about that? The first one I choose. Wow, doesn't usually go that well. All right, I believe this is a picture of 11. And could you read me the wording on that one?
Sure. So use a network to find whether it is possible to draw a sensible connected broken line that crosses each line segment up to 3 below exactly once. The line segments are those that go through section down.
Thanks. So I made this drawing, and I drew on those doors. What I'm trying to show you is you're supposed to be able to cross each line segment. So what I did is I kind of built in a fake door in each line segment. Does that make any sense? You know, every line segment I made a door. Okay. And then I did my network thing. By that I mean I put on a dot for every room. And don't forget, you need a room for outside, so I happen to call that E. And then you start running through and say, all right, where can I go from room D? And the answer is, well, I can go outside 1, 2, 3 different ways. Can you see that? So I had to draw three strands from D to E. I could also go from D to B, and I could also go from D to C. And I think that wraps up D. And then I went to room C, did the same thing. Got this thing, and I ran my counts. And what do I have? 2 odd vertices. Therefore, according to Euler's law, this should be possible. And so the answer is yes.
My other question, which you already answered it, was, so if there's a box or whatever they're called,
Right.
if there's more than one opening, those both count.
Yeah. So like here,
Because that wasn't really clear to me, I guess, like before. So
you know, we didn't have a lot of multiples. I think that's why it maybe didn't become so clear to you. In the examples, I was just thinking, were there multiple doors going outside? Maybe once. It wasn't as obvious.
So each doorway is
Each-
a possibility.
Right, so like this tells me there's 3 ways to get outside. And so I really need 3 different paths from D to E. Yeah, that's a key question to be able to be successful. Right. Yeah, I'm not sure we made that real clear last time. Sorry, still got a little tickle in there. Feels a lot better, but... Other questions? Yes. Okay. First of all, the regular parallel postulate just says this. You have a line, you have a point off the line. And if this is all sitting in a plane, through the tip of my finger, there is only one possible line that could be drawn. There's only one possible line that could be drawn through my finger that still lays on the chalkboard that is parallel to my arm. There's only one. That's the parallel postulate. Okay, now when you change to a sphere, what does a line become? I got to think about this again. It's like a line of longitude, which is not a line at all, it's a circle, right? Okay, so let's think about this. So we have a line of longitude. Now we take a point off. Okay, how many lines, now we're on the surface of a sphere. I know you got to imagine all of this because I don't have a holographic chalkboard yet. It's on order. It's not. There is no such thing. But anyway, got this line of longitude. There's this point over here. How many other lines of longitude can be parallel to this line and still go through that point? Well, see, here's the problem. How many great circles are parallel to this one that are lines of longitude? Answer? None. Why not? Because doesn't every line of longitude intersect at the two poles? So in that crazy geometry, there are no parallel lines. Weird. Okay, and now if you go on this upside down funnel thing, and you take a line, which is something that's going up that kind of the funnel channel, now, ironically, all lines are parallel, which is really weird. And so that's what messes up the different parallel postulates. Actually, all I really care that you remember is the regular one that in plane geometry, the one that you learned in high school, everything's on a plane, and if you have one line and a point off of it, there is only one possible line in that plane that can be parallel and go through that point. Really, but just beware, there are others. If you have these other strange surface geometries, that's good enough. Yep. Sure. Okay, 13. And what page are you on? 572. Thank you. 572, number 13. Oh yeah, it's one of those drawings again. Okay, I'm going to skip drawing the floor plan in the book, but I'm going to go right to trying to draw a network diagram for that. So I need a letter for each room, and I also need a letter for the outside. So let's just get this down. We're doing number 13. And I've got letter A. What is it? ABC across the top. D, E, F parallel to it on the bottom. And then I've got, I don't know, let's call it room O for the outside over here. Doesn't matter where you put it. Okay, room A, where can I go? I can go outside one way. I can also go to room B and to room D. Okay, let's move to room B. Where can I go? You can go to A, I've already got that. You can also go to C. Is that it? Yep. Room C, you can go to B, which I already have, and you can go down to F. Room F, you can go to C, which I already have. You can go to E, and you can also go outside. Okay. Room E, I can go to F and E. D. F and D. And that's it. Room D, you can go to E and A. And I don't think I've missed anything. I think I've got it. Now, run a count at each vertex. 2 odd vertices, therefore, it's a go. It's traversable. And that's the end of 13. Any others you'd like to look at? Maybe time for one more? Yeah.
It has more odd verses. If it has more evens than odds,
It doesn't really matter how many evens there are. The only thing that matters is that there's 0 or 2 odds.
right.
So actually, we don't really care how many evens there are. The key count is how many odd vertices. And if there are 0 or 2, it's a go. Anything else, too bad. Can't do it. Okay. Well, we better get going. This is a challenging lesson to get in. We'll see how I do. This is the lesson, 8-7, Chaos and Fractals. And I thought I'd put a fractal on the screen while the title page is up there. Fractals are really unique geometric things. Chaos and fractals. Okay. I guess that's a problem from yesterday. I should have had that in a different place. Scoot that up here. Okay. I'm going to do my best at trying to... I can only show you what this is today, kind of by getting in there and doing it, and teaching you while we're doing it. But I am going to define a couple of words to get this thing rolling. I'm sure you've heard the word, or a portion of the word, iterate. I'm sure you've heard speakers say, let me reiterate. What's the meaning of that when they use it in that context? Rephrase, or maybe kind of a repeat, but with a slight change. This idea of repeating is the key concept, and that's what it's going to mean here in mathematics. You notice I've got this called a noun, but this is also a verb. You know, we're going to speak of an iterate as a noun, and I'll show you some iterates today. And you can say, I want you to iterate that. And then in that context, it's a verb. Another form in noun form is, we sometimes call an iterate an iteration. So just kind of getting some of the language straight, you're gonna hear iterate, iteration, and to iterate means to like rehash it, do it over again. It's almost like what? Hard to explain. Let's get into it. We're going to do some iteration right now. Some iterations are geometric, and some are arithmetic. So in other words, you can do iterations on geometric shapes, which I'm going to do first. You can also do iterations on mathematical formulas. And today the goal is to do some of each. So I'm going to begin with what's supposed to be 4 equal line segments. I had to sketch those as best as I could freehand because I need to break them up, and it's just a long story. I just couldn't do it any other way. But anyway, do you see how those appear to be 4 equal sides? Okay. Now, here's what the rule is going to be for iteration. Take each of the 4 line segments and first divide them up into 3 parts. Okay? So in other words, make 2 marks so that this is divided into approximately 3 equal pieces. And I think you'll agree it looks like I roughly have that in 3 equal pieces, don't I? Okay? Now do the same with each line segment.
Okay? Now, erase, I know you may not have a eraser, but erase the central part. And then, on each one of those little openings, make a little equilateral triangular bulge out above. And so, here's how it looks after iteration 1. Now, if you look closely, I know you're still trying to recover and get to that point. How many little line segments do we have now? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 16, right? Okay, now with each of the remaining line segments, do it again. This is iteration 2. Do it again. So, now this gets kind of hard to do, especially with the tools I've got, but we're going to try it anyway. Okay, divide each part into 3. And here's where it's going to be really hard for me. I'm supposed to erase those. My eraser's not that precise, but yeah, I'm going to just hang it up on this. Anyway, the next step is draw triangular equilateral jutouts, whatever you call them. Whoops. And it should start looking something like that. Okay, now, I apologize, I don't have better tools, but I just can't get any more precise than that. I'm sure you can do better with a pencil. Now, can you imagine if all right, now go on and do iteration 3. Well, now you got a lot more segments, right? And now, if you could imagine, if you had really supervision and really sharp tools, you could keep doing this forever. Okay? Each time we do it over again, we're doing what's called an iteration. The resulting object is called a fractal. So when you do geometric iteration, the result is called a fractal. And these are really cool objects. Now, first let me just show you okay, that one on the bottom of the page is an animation of what we were just working on. I mean, here's how it started off, right? We had these sides, then we divided each of those, and we should have had an edge on the top that looked like that. And when you do it again, it looks like that. And if you keep doing it and keep zooming in, and think of it as, yeah, infinite ability, you can zoom in forever. Yeah, so that's a fractal. Don't stare at it too long. But that's the same thing, just keep zooming in on it. You know, actually, yeah. You know, what used to look like this, isn't that really right here now? And isn't there another one right here? Only if you zoomed in, it would look just as and you can see how it just keeps repeating and repeating and repeating. Okay, well, that's a fractal. We're going to do another fractal. Okay, this time we begin with a square. And I tried to make it as big as I could because I need the space. Okay, we're going to do something similar to what we just did a few minutes ago. I want you to divide, well, first I got to give you a chance to make a square. I'll give you a clue. What? The bigger, the better. I'll give you a clue. We need to divide the square sides into 3 equal parts again. So I made mine 12 notches by 12 notches because 12 is a nice divisible by 3 number. But so anyway, what I'm going to do, iteration 1, divide each side into 3 equal parts. 1, 2, 3, 4. 1, 2, 3, 4. So divide each side into 3 equal parts. Once again, erase the central part. Okay. Now, on each opening, construct a square going to the inside. That one's supposed to be straight, boys. Sometimes I have to do everything freehand for this to work, so I wind up with some rather ugly looking things here. That's not too bad. Incredibly bad. Failing kindergarten art up here. Okay, well, let me just repeat what I did. I took the big square, divided each side into 3 parts, and then the central part I erased, and I built a square going toward the inside of the square on each one of those openings. Result? This is the result of iteration 1. Everybody with me? Now, we had 1 square to begin with. How many squares do we have now? We actually have 5. So on iteration 2, now I'm not going to make you do this on all 5. Okay, pick one. Like, let's take the central one. Take the central one and do the same thing again. Actually, you should do it on all of them, but we don't have time. Okay, so on the central one, divide each side into 3 equal parts. Erase the central part of that. A little too happy there. And then build a square going toward the inside. It should look something like that, but mine isn't real equal, but. Okay. Once again, what did it do with this one square here? It turned it into 5. If I had done it to all of them, it would have taken my 5 and turned it into 25. So if I had done this all 5 times, wouldn't I have 25? Now can you imagine doing iteration again? But, I mean, emphasis on the word imagine. You can at least picture that it could be done again. And now, I just have to do it 25 times. Okay, this is another example of an iteration. And therefore, it's a fractal. Okay, here's one that's a little bit simpler. By the way, here's one I did last year, only I did the second iteration on the one in the bottom right. Here's a little easier one. Let's just find the midpoints of each side. And then connect them. Let's see, what do we need? I'll use red. Connect the 3 points from the midpoints. Okay, we started with one triangle. How many do we have now? Yeah, depending on how you count, we have got one big one and we have, what, 4 little ones? So let's just take the little ones. Take each of the little ones, 4 of them, and do the same thing. Midpoints. Connect them. Whoops, that didn't quite turn out right. Almost looks like some kind of art project. Okay, there's iteration 2. Now how many triangles do we have? 16. Now you can do it again, and we're not going to, but that's another example of a fractal. Okay, so you get the concept of this. And technically, I mean, for it really to be a fractal, I should keep doing this until, I have this thing keep zooming in and I could keep going and doing greater detail. Okay, we're going to switch gears now. Now I'm going to show you an arithmetic iteration. Okay? In the box is the equation we are going to begin with. And that's supposed to read y equals 2.5 times x times the quantity 1 minus x. Y equals 2.5 times x times the quantity 1 minus x. And here's the deal. To begin with, and you will always be told this, we're going to give you a starting point for x. The starting point in this problem is x equals 0.5. Okay, so in our first iteration, we're going to plug in 0.5 for x. We do that right here. I call this 1y1 because this is our iteration number 1. 2.5, there it is, plug in the x, times the quantity 1 minus, and there it is again, the x. Okay, I'm going to save you the calculation. The answer comes out to 0.625. Okay, no big deal. Now, watch this, because this is the key. How do you do a second iteration? And the answer is you take your previous answer, 0.625, and you make that your new x. So do you notice in iteration 2, I take the same equation, 2.5, but in place of x, I now put my previous answer, 0.625. Both places x is, I have to plug in a 0.625. Okay? What do I get for an answer? This time I get, turns out to be 0.586. Okay? Third iteration. Do it again, only this time in place of x, put your latest answer. Okay, so at least I've done enough. You should see that aren't we doing this iteration again? We're just kind of keep doing it over and over. Okay, now those answers sometimes have a pattern to them. And I've got to go to the website and show you this. I've got a tool here that will help you with this, so you don't have to sit there and crank calculations out. If you go to My WLC and go to our course, Chapter 8, (8.7), you'll see that there is a link. It says Iterates Excel file. Okay, if you click on that, it'll open this file in Excel. And I've got some nice things in here that will save you a lot of time. Okay, let's go to the top. Okay, here's the spreadsheet for you. You notice it tells you here's the equation. It's in the form. Let me get this out of the way so you can read it. Y equals k times x times the quantity 1 minus x. In other words, k is whatever problem it gave you. In this problem, what did we do? K was 2.5. So I'm going to go in here, and this is the only thing you have to type in, the k. And then the only other thing you have to type in is what did they want us to start with for x? On that problem, it was 0.5. Okay. Now, there's iterate 1, there's iterate 2, there's iterate 3, and in fact, I've got the iterates done all the way down to 200. Okay, just so you know, they're down there. Now, what's interesting is, do you see any pattern if you look in the column of iterates? And the answer is, yeah, we get stuck on 0.6. We have a special name for numbers you get stuck on. Okay? They're called attractors. Not as in a John Deere, but like in the word attraction. Not, sorry. You got the picture. A-T-T-R-A-C-T-O-R. Attractor. Something that attracts things to it. Kind of like a magnet. So 0.6 is called an attractor for this particular problem. Okay. So now I'm going to teach you some more terminologies. Sometimes there's more than one attractor. Sometimes there are no attractors. And when that happens, we say we have chaos. When there are no attractors, we say we have chaos. And there's a term that was in the title of the lesson. You remember? Chaos and fractals. When there are no attractors, we have chaos. Sometimes you can have multiple attractors. Let me show you another example. In fact, should we take another one from the book? Okay, this time let's make K3. And let's have our starting value be 0.2. Okay, look at the Y's now, and you may have to do some scrolling here. Do you see any patterns? Do you see any attractors? And the answer is no, not yet. So let's keep looking. Sometimes it takes a while. Aha! Now they finally show up. Do you see we have, in this case, two of them, and they are 0.699 and 0.631. And it took us 41 iterations, no, it took us 40 iterations before they kind of sifted themselves out. You see how up here we still didn't have that pattern. But starting here, we have 2 attractors. Sometimes you'll have 5 attractors or 4, and you got. So here's what I did. I made this spreadsheet up so that you guys could concentrate on looking for the patterns and not having to do 12,000 calculations. Okay, which is the main emphasis. Okay, so all you're gonna do again is input K and what the starting X is, and then just open your eyes and look, and you may have to do some scrolling. And if you see nothing happening, absolutely nothing, we have chaos. Or you may have 1 attractor. Here we have 2. You may have 4. You could even, you're not going to have too many more than that. Maybe 5 would be about the max. Okay. So please be aware, you're going to need that file, and you're going to need to use Excel in order to finish this up. But so this is not going to be multiplication anesthesia. It's going to be, hopefully, I use the spreadsheet, and it's going to be pattern searching primarily, and that's a lot of what chaos and fractals is. Now, there's a surprise too in this whole thing. I think total surprise. So first of all, let me just comment. You know that Friday, I told you this, I'm giving you a presentation Friday, and guess what? I'm going to talk to you about that particular fractal. The very famous fractal, and so that's the topic Friday. Now, here we go, I think. Nope, I got to load it. It's an attachment. Yes. You're going to be really surprised at some of the fractals I'm going to show you. And I don't have a whole lot of time, so I may have to zip here. I think I've shown you this one before, haven't I? No? Sorry, too many classes in my head. Sorry, I'm pushing the system pretty hard here. Here we go. Well, first of all, these are both fractals. I mean, what you've got here is a picture of somebody standing in front of a mirror. You know the old 2-mirror trick. You guys have probably all done that, right? Bathroom mirror, and you hold up a mirror to see the back of your head. And eventually what happens is the 2 mirrors start battling, right? And it goes in and then those are fractals. And then what you saw here was kind of a video of another one. Did you see that? Or did I draw your attention? Okay. Now, next. This is a fractal. And one of the unique things about a fractal is you can keep going in on it forever. So what I'm going to do is highlight a section with a square or a rectangle, and the next picture is going to be framed that way. Okay, now we're going to zoom in on that. Okay, now we'll zoom in on that. Okay, and we're just going to keep picking a new part and zooming in, and there's forever more detail. You get the idea here? In a true fractal, you can do that forever. Okay, now,
Here's the real shocker. That's a fractal. It's all mathematics. That is not a photograph. And a good share of, there's a fair number of movie segments that are today done with fractals. Actually, you actually can create very realistic scenery strictly with numbers and strictly with fractal equations. This is an example of one. I've got several.
These are all done with, you can, by the way, there's free software available that you can create these on your own. So it's just actually, you wouldn't believe you were looking at mathematics, but you are. And I just got to show you one more, and then I got to get you out of here. I find this very fascinating. A coastline, that is where the land meets water, no matter where you are, on Lake Michigan or on the ocean, what happens is, if you look at the coastline real closely, what do you see? A jagged edge of some kind. And if you look at it even more closely, what do you see? You see more detail on the zigzag. And if you look at it even more closely, what do you see? Even more zigzag. It's the same thing we were just looking at. In fact, these two guys in, I can't remember where. France? Where does it say that? Yeah, second paragraph. These two French guys found out that fractal coastlines, which is what we have, are the best at damping waves. That is, they do the best job of calming the wave down when it strikes the coast. And so if you have all these little jaggies, it helps calm the waves down. And that's exactly the way it was created. I just find that real interesting. Don't forget, Friday presentation, bring your notebooks. Sorry I kept you a little late. Thank you very much. Take care.